It's 1 o'clock in my world, so if it's okay with everyone, I'll get started. So today I wanted to talk about galaxy morphometrics, and I just realized that I used the old one here. So fourth one, morphometrics. There now. Abide when a slide is wrong. And so we talked about visual morphology classification, the kind of thing that Hubble and Sandage and Vauquelin did. We talked about subgalaxy phenomena like bars and bulges and ANSI and spiral arms. We talked about how we do this now visually through cloud classification, essentially having lots of votes instead of just single experts classifying things. We still do the single expert classifying, by the way. I mean, that's still being done, but we also now have a group consensus classification, if you will. So the last thing that do I still have a, oh, okay. And so we've gone from these gentlemen with pipes in black and white and sketches to this tuning fork of Hubble's that I have this thing in the middle here that I need to go and move out of the way. There we go. To the Hubble tuning fork, and this is how we've been discussing Hubble's tuning fork is how we've been discussing galaxy morphology. So that's the terminology we've been using. The ones basically to the left of S0 we keep calling early type galaxies, and to the right of S0 we call late type galaxies. I find that incredibly confusing, but it is a terminology that has stuck, and so I'm mentioning this because then if you see, as soon as you see a paper where it says like ETGs, I mean early type galaxies, but I try to avoid this as much as possible. I'd like to be descriptive. So this is sort of what we think of it now, like ellipticals, lenticulars, barred and unbarred galaxies. So we have a morphological classification, and thanks to the Galaxy Zoo, we have a way where majority of people think this is an SB. Like, so okay, that's probably an SB galaxy. But what we really like to do is turn that complex morphology that we see in the left here and turn that disk with all the spiral arms, the bar and the bulge and everything into a few quantitative numbers. And the reason for that is that we're not going to deal with single galaxies. We're not going to deal with a few hundred galaxies where you can, look at all of them yourselves. If you look down to what's coming down the pike, it is really a lot of images. So the Sloan Digital Sky Survey has taken a digital picture in 5 colors of about a third of the sky. We're easily filling in the rest right now with Sky Mapper and Dark Energy Survey. So we have essentially a 5-color full sky map. That's already millions of galaxies. And then with something like the Vera Rubin Observatory, we're going to go deeper. With Euclid, we're going to the near infrared. With SKA, we're going to radio. All these things are going to produce oodles of galaxy images. And so we'd like to turn that into some quantifiable number rather than just saying it's an SA. So where does this term morphometrics come from? It's a term from biology. Biology has been doing this for a while because they also are dealing with weirdly shaped things that they have to go and separate out, and they'd like to quantify these things. So what they did is simply identify points in the morphology of various beasts. Things like, well, how you see the fish over here is like the tip of the nose and the end of the gills. Like that's a clear point that you can mark on a fish or a photo of a fish, and so you can mark those things and see how far those things are apart and how they relate to each other. And so you have a couple of those points, you turn that into numbers. So you turn the complex morphology, the entire shape of a fish, into a couple of connected dots. So yeah, you throw a bit of the information away. You have to be aware of that, but you hopefully keep the relevant part, the part that allows you to identify one kind of fish, or like an adult from an adolescent, by having like, oh yeah, those two numbers have increased. So what you see on the left there, I think, are bat wings. So they basically have the same bone connections, and it's like, yeah, there's a points. You can put those, you can mark those points on a picture. So it's also not so invasive. So you could just do that based on like surveillance photos and stuff like that. So we're trying to do that with galaxies. So there's a whole bunch of these different schemes how we can turn one single image of a galaxy into a bunch of numbers. And the first one is called CAS, concentration, asymmetry, and smoothness. So concentration is simply saying, like, I've got two apertures, I've got two circles that I count the amount of light in. I have one that encloses about 20% of the light, and I have one that encloses 80% of the light. And the ratio between those two, I take the log of that times 5, that's my concentration index. So the higher it goes, the bigger our 80 is with respect to R20. So the more spread out the whole thing is. And so the more they are similar, the lower the value. So you need to get a feel for which way the concentration index goes. But that's one of the indices. It's pretty easy to compute. It kind of comes out of several different software. The other one that you can do is you take the image and you flip it. You rotate it 180 degrees, and then you subtract the two. And the difference between those is essentially all the little stuff that isn't perfectly mimicked on the other flip side of that galaxy. So if a galaxy is perfectly round and smooth, you have a very low asymmetry, because essentially the left side subtracts the right side perfectly. However, as soon as you have, like, I don't know, star formation regions, spiral arms that aren't perfectly symmetric, then asymmetry starts to climb. And the last one is, and so that's where you take the same image and you smooth it with a certain kernel. So that's a choice that you have to make. You have to smooth the image a little bit, and you subtract the smooth version from the original image, and then you're kind of left with like all the little details that were smoothed out. And so it is a level of smoothness. Again, if you have an elliptical galaxy, you subtract the same from each other, you basically have hardly anything left. That last one is based on a technique called unsharp masking, which, if you allow me a sidebar, I find incredibly cool. What they used to do with these photometric plates is that they took a picture, and the photometric plates are, a certain thickness. They're actually quite thick glass plates. And so they took the picture, and then if you then developed it and then flipped it, it was a little out of focus. And so they basically had a smooth version of it, and then they exposed a new one behind it. And so they could actually do this unsharp masking. They masked the smooth part of the image, but only if it was like a little detail that would come through. And so that's a kind of way where you could use photographic plates as like image processors, which I thought was, how do you even think of that? But so this technique has been around for a while. Another way to do this is called the Gini parameter. The Gini parameter is an economic measure. So again, we've been borrowing from other fields. Gini was an Italian economist. Don't look him up, don't Google him, but it is the kind of thing that is quite useful, because if you have a population where everybody has a certain fraction of a thing, so let's say we have the population of Kentucky, and we can say how much does everybody have from the total wealth of the Commonwealth, right? So how does everybody have the same percentage? In which case, you see the fraction of pixels, like that's the population. So the fraction of the population and the fraction of the total amount of money. So if that's equal, everybody has an equal share, then basically that's a straight line going up. However, if one person has all the wealth in Kentucky and nobody else has anything, that basically means that you can go along the ordered line of like, line everybody up with like how much money they have. And so you have nothing of all the wealth, and then boom, it suddenly spikes. So it's a good indication of how the wealth in a place is distributed. And so you can actually compare, like, say, a small nation to a bigger, much bigger nation and use it to boil it down to just one number. So G is 0, there is no difference, there's absolute equality, and G is 1, that's absolute inequality. Basically, all nations fall somewhere in between, and so this is what the UN, for example, uses to rank nations on level of wealth equality. So you turn something that's highly complex into a single number, right? So that's sort of what this morphometrics is all about. You turn something like it's a number of pixels, fraction of the pixels that you have, and then the fraction of flux that you that each pixel has. So suppose you have like a completely blank image, picture of a blank page, that kind of thing. Each pixel has the equal amount of flux. So basically you get Gini of 0. As soon as you start having structure in there, some pixels are brighter than other pixels, you start going closer to G is 1. If you have a blank piece of, like a blank image with just a infinitely bright pixel in the middle, then you have G is 1. So basically galaxies have also split the difference. They're somewhere between 0 and 1. And I think of that as, if you think of it as an economic indicator, you know, the Smurfs, they share everything, so that's a Gini of 0. And if you are Kim Jong-il, you have all the wealth and nobody else has anything, so that's when you're, that's a Gini of 1. So another part of that Gini M20 space is M20. And so that's the second order moment. So bear with me for a second. If you have a picture like you have on the left here, and you have a center of the galaxy and you have a pixel somewhere, and that pixel is a certain distance from the center of the galaxy, and it has a certain amount of flux. So you take the second order moment. So you multiply each pixel's flux by the radius squared. And so you sum all that together, and that's the total M20. So that's the total moment, second order moment. And then you say, okay, well, what happens to the 20% brightest pixels in the entire thing? So where are they? And so if you rank all the pixels, you can say, okay, this is where the 20% brightest pixels are, and how much second order moment is sitting in that. And so that's the relative second order moment of the brightest component. So suppose you have like an AGN sitting in the center and that all the flux is coming out of that. That's a really low M20 because all the brightest pixels are sitting in the middle. However, if you have like a star-forming disk, then the bright pixels can be all over the disk, and so they could be much further away, and that's much higher M20 values. So this M20 values, it's negative. It basically goes from -3 to about to 0. And so that's another parameter that we can use. So CAS and M20 are the two that I'm going to discuss. There's a couple more, and once in a while somebody thinks of a new one. So essentially we keep adding more morphometrics, and depending what you want to do, they might be useful. I'm happy to talk about it more, but I'm just talking about CAS and M20 today because those are the ones that really got established. CAS got established in 2003 by Chris Consolas. So he did this on a nearby galaxy sample. And so his question was, is this a good way to classify galaxies automatically along the Hubble tuning fork? So instead of doing this, by eye with hundreds of galaxies, if I simply get the new images, run it through my software, it has a certain CAS value, and that means it's a, SA. And how well does that change with wavelength? So that's the other part, right, where he was trying to figure that out. So it looked really promising. The red galaxies are ellipticals, and the blue galaxies are regulars, and and spirals, and then there's some ULERGs. So those are the ultra luminous infrared galaxies. Those are often mergers, and it looks like all these different classes are separating out in this parameter space pretty well. I mean, there's some mixing that's to be expected, but we can give you like a probability that way. And so the second part of that was that, hey, if I do this in low redshift, I can see how galaxies evolve if I do this at higher redshift. And so it's easily computed. Maybe this is something that we can end up using a lot for morphology. Jennifer Lotz in 2004 published her paper with the GeM20 method. And yep, same idea. Like you have disk galaxies on one side, spheroidals on the other. So you like see the little circles of the spheroidals. You have the triangles that are dwarf spheroidals, and then the X's are disk galaxies. So they seem to separate out pretty well. And then mergers are above that dashed line. So it might also be a good way to identify merging galaxies. So mergers happen when, for example, two disk galaxies smash into each other. So then they move morphologically above that line for a while, and then they come back down as a spheroidal, right? So that like we can actually trace passages through morphology space using GeM20 or the CAS method. So we got really excited because this would be a great morphological way, so cheap, we just need an image, to trace how much galaxies merge over different epochs. We just look back in time and classify everything along CAS or GeM20 and see how many lie above the line. So these broad classes seem to work great, and they do seem to do mergers, right? So at the bottom you have lots of original picture, and at the top we have a more recent paper where we're not only looking at data. So on the left side is the actual data between redshift 0.2 and 0.4, but also a direct comparison what simulations predict, like what the morphology in simulations, like these big hydrodynamical simulations. You throw in gravity, you have a prescription for star formation, you say this is how they coalesce, and then you can see if you got your morphologies ballpark right. And it's like, well, that looks really convincing, thank you. So it's a quantitative way to compare against simulations. It's a quantitative way to say, hey, this galaxy, it looks like it's merging because it's above my line. A quantitative way to say this is either a spheroidal or a disk galaxy. So you can start classifying things rather quickly. And so that's a really attractive way to do science. But there are a couple of questions. So first one is, how long does a merger stay above that line, right? So if it just, dips above it and then, shoots back down, yeah, you see one or two that you happen to catch in the act, but everything else is, is hiding among the disk or the spheroidals. So it's actually, you don't see it for very long. So you need to know how long they stay above that line. If you want to turn the merger fraction, so how many galaxies do I see merging this way, into a merger rate, how fast are galaxies actually merging over time? And so that's what you need to do you need to calibrate this very carefully with simulations. So that's what Jennifer Lotz did in 2008 and 2010. She published a bunch of papers on this series of simulations where they took two spiral galaxies to the same mass, to different mass ranges, so 1:3 mass ratio, 1:10 mass ratio, and just watched how long each of them, how they changed over time. So there's a whole suite of simulations where different angles where they hit each other, different angles where we view the whole thing, and then they process this so that we actually see these in the Sloan Digital Sky Survey filters. Now, as you look at these galaxies, you go like, we're not quite in the uncanny valley. You kind of look at this and go like, yeah, I can sort of tell that these are fake galaxies, right? This is getting better and better every year, but we're still at the point where we look at this and go like, yeah, the resolution is not quite there. I'm not sure what it is, but it looks a little too good, something like that. There's not quite enough dust maybe hiding some of the star formation. There's a little things that we can still tweak, but it looks pretty convincing. Let's see if we can actually play this. Is it actually? Yes. Okay, so they of course make this wonderful, not only the simulation, but if you make simulations like that, the best part you can do is make a whole thing into a movie, because that's what we're looking at. We're looking at the morphology of galaxies changing over time and how they look in different filters. So the blue filters, for example, definitely show this merger effect much clearer than the redder filters, because star formation that happens, okay, I forgot to turn the sound off on that one. and I can't talk over. That's the one thing that I needed to do. And so I'll, this way I can talk over it. And so you start with these simulations. Yes, okay. So this was a huge project because not only the parameter space, as you can imagine, is enormous. Not only did you have different mass ranges, you had, you know, the one-to-one merger, basically take a Milky Way and take another Milky Way and smash them together, but then all the different incident angles, right? What happens if they hit edge on? What happens if they hit at a different angle? What happens if they kind of skim each other? So you have a range of parameters, like what's the impact angle? But then also the mass ranges, right? What happens if I take a small galaxy and hit a bigger galaxy with that? Not only that, they decided to get quite, this was ambitious. So what happens if I stick a lot more gas in the Milky Way, for example? Suddenly I have way more fuel. So here you can see that, you know, if that happens, a lot of star formation happens in a very short amount of time. So in the blue, this thing looks completely different from a normal spiral galaxy. However, in the red, it starts to resemble a normal disk quickly because you don't see the star formation as well, and before you know it, the spiral arms are, you know, back to being regular. But oh, there we go. By the second passage, you are definitely got tidal tails. You've got lots of debris. You've got another burst of star formation. So in the blue, you see it early, and in the red, you see this like later. So it also happens. You're depending on your window, you see the morphology change at different epochs of the merger. So the whole thing takes like 2.5, 3 billion years. The whole simulation is 3 billion years, but you know the first billion years is really easy to spot the hairs, the dust. So they also threw in dust, which makes the whole thing a lot more complicated because it reddens everything and just hides a lot of the dust. So this was the part where it really got computationally expensive, where they had to turn those n-body simulations and that big parameter space and then post-process it so that it actually had stellar evolution and dust absorption. So very impressive. So without dust, it looks like this. That's great. But with dust, you know, the morphology changes, especially in the center. Honestly, I'm a dust kind of person. So I would say like, yeah, there's probably more dust in the outskirts. So I like the processing already, but it could probably do with a little more diffuse dust everywhere. But that's neither here nor there. So yes,
I'm listening to a lecture.
Okay, so the big trick here is that you have these morphologies and you're sensitive to different time, like in different colors at different times. And now, for example, you could also see this whole thing in gas, like what happens if I look at the gas morphology, right? So that's what we're seeing here. And suddenly we get these tails way early, we get, you know, much wilder geometries. And so you go like, oh, I can definitely see it in there. The trick is that gas morphology is really hard to do because you have to do that with radio astronomy. So depending on your, you know, glasses that you're looking at a merger, it will look disturbed at different points of the merger and for different timescales of the merger. So you need to calibrate it very carefully. So suppose you look at B band, so that's a blue filter. Okay, I then know like for half a gig a year, the merger is like clearly merging. They're completely separate. If I'm looking at K band, they look like half a gig a year, but it's, you know, almost at the end that it's pretty clear that it's a merger. So if you have these morphometrics, they could identify fractions pretty well. The merger rate is another trick to translate the whole thing into a merger rate, but you can do it. And so it's pretty neat because once you have that, you can say, okay, well, as I look at the merger rates for galaxies, so these are the simulations, and then you got like concentration, M20, Gini, asymmetry. It's pretty easy to compute all of those for these. And then you see that there's like this double spike. Like there's basically every time there's a close passage, that's when they really look different. So you can morphologically identify them as mergers. You need to do this anyway. If you do this with Galaxy Zoo, for example, things don't look like a merger for like a big part of the merger time. Most of the time, they just look like a close pair of spiral galaxies. Maybe they've skimmed each other, maybe not. But there's these two peaks. There's basically these two flybys where they really start to change. Like you see it as galaxies. First pass, max separation is when they sort of basically coalesce back to normal. Second pass is when the real big spike happens, and the merger happens right after that. And then afterward, they're a post-merger, but even post-merger galaxies sort of look like normal galaxies, very close again in the morphological spaces. And so they try to look at different gas fractions, because the star formation gets triggered by the interaction, you get big loops of gas somewhere. And so you look for these loops of gas and loops of star formation. So, okay, the more gas rich, the more deformed a galaxy, disk galaxy becomes. The other option is that you can do is you take the different mass ratios. So that actually works pretty well. And this is now a small industry basically in galaxies surveys, where you have that M20 Gini parameter space, and then you go and intercompare it with all the other classifications that you have. For example, on the right here is Pearson's comparison. So he computed for the entire gamma survey. So this is several tens of thousands of galaxies, something like 50,000 galaxies, computed M20 and Gini for them, but then labeled everything with the Galaxy Zoo merger fraction. So basically how many people said, oh, this galaxy is merging. And so most of the time, neither. It says like, yeah, there's nothing going on. And so you see that most of the people seem to say like, yeah, neither for the majority, but just above that line from the green or the yellow line from Jennifer Lutz, like, yep, that's where actually the fraction goes lower, and people start to think like, yeah, that could be a merger. And then you can also look at an expert classification from Dark, for example. It's like, where do those galaxies that he identified as merging galaxies lie? And like you realize that the majority lie below the line. So it's quite hard to calibrate and get like different techniques to agree with each other. You can also do that with asymmetry and smoothness. So again, this is the line, the orange line is the one from Chris Consolis. And this time the Dark, very morphologically disturbed galaxies do lie above that line, and the Galaxy Zoo seems to agree with that as well, saying like, yep, those are all merging galaxies. Of course, you still have a lot of contamination, so you can sort of do this as a overall statistics, hoping to calibrate for like how much contamination you have, how much cross classification. So we'll talk about this kind of thing because this is starting to touch on machine learning, like how clean a sample, how much are you missing. These are the kind of classification challenges that machine learning, thrives on. So we'll talk about that a little bit in the last class as well. But what you want to take away from this is that these classifications do work, provided you're sort of in the same survey. If they all have all images have the same characteristics with the same wavelength or the same spatial resolution, meaning actual physical resolution, and you can see the same level of details among all the galaxies, so they have to be at roughly the same distance as well, and then it works in a statistical sense. So. However, this parameter space is far from orthogonal, right? So these two different people came up with two different classification schemes. So concentration and Gini are pretty, they're not orthogonal. If I make a galaxy more concentrated, the Gini changes as well. And if I make a galaxy more asymmetric, its M20 tends to change as well. So these things are not one-on-one correlations, but they definitely know about each other. So it's not an orthogonal parameter space. So Claudia Scarlata in 2008 decided to go like, well, I can do a principal component analysis and see how many independent axes do I have in this parameter space for like this whole galaxy survey. So the Zurich estimator of galaxy type, ZEST, spectral spiral types. ZEST. She came up with ZEST as the acronym. And so this is the three-dimensional principal component space that she ended up with. And the brilliant part is that it does a good job of star galaxy separation. Just getting rid of stars is already a big benefit of this. You can find inclination effects, and you can find bigger bulges and smaller bulges. So you can actually discriminate Hubble type maybe, but turning it into a principal component parameter space, where essentially all the individual concentration, asymmetry, Gini, etc. You turn it into like, actually, I have three independent eigen vectors for this galaxy. Chris Gonsalves did something similar in 2006. And so you can think of this as eigengalaxies. Like if you are, if you've done quantum mechanics and like eigenvectors, this is the exact same idea. So there are some caveats. I mean, it looks good, and we can start. It's a parameter space that helps us separate out galaxy morphology. And rather than Sirsic index, which is for the entire galaxy disk, right? It starts to take smaller things into account. It actually takes spiral structure or bars or bulges, like these sub-galaxy scale morphological features. They do weigh into morphometrics. So that's good, but it works great within the same survey. And I cannot overstate this particular part of the caveat. It works great within the same data set. So you can separate things out, you can identify unique features, you can do that, provided it has all the same characteristics, same image depth, same physical resolution. So a kiloparsec bar is equally resolved across the survey, and it has to be the same wavelength. As soon as you go from one survey to the next, which is really the thing that we wanted to do, we wanted to go from a low redshift survey to a high redshift survey and intercompare. We wanted to go from, say, the nearby galaxy survey that Chris and Jennifer did, and then compare that to the Hubble Deep Field, for example. That gets a lot harder because all those things change, and that means that all these values, all the normalization changes subtly, and sometimes galaxies that you would otherwise would have, for instance, classified as a merger now basically get smoothed or moved, and so they drop below the line. So high redshift, for example, you observe a much bluer rest frame wavelength. The wavelength that you observe is, for example, ultraviolet, but by the time it gets to you, it's optical. And so you need to compare to a UV image locally if you want to find the same kind of things. So you have to match both image depth, physical resolution, and wavelength before you can say something intelligent about, say, the merger fractions, how they compare up, the level of disks that you see, the number of spheroidals that you see. Because if you just run it through raw and go like, yeah, look, I'm seeing, I don't see any disk galaxies anymore at high redshifts. It's like, yeah, that's because your image depth was different, or because you looked at a rest frame ultraviolet, and then if you look at a rest frame ultraviolet image of disk galaxies nearby, they're basically a collection of little blobs. And you looked at those as individual sources rather than a single disk. So there's a lot of caveats are hiding in the corner, and there's something that one of them will bite you if you just start naively comparing. That said, we're not just getting a lot more ultraviolet images, we're not getting a lot more UV images, we're also getting loads and loads more images in the radio, and especially in H1. So this is a 21 centimeter emission line, and so you can map nearby galaxies in their gas and their hydrogen. And so that's what you see here. The blue is the gas, that's the atomic hydrogen, and the orange and yellowish is the stars. So that's what we typically think of as the galaxy, because we're optical. Our eyes are optical instruments, so we have an optical bias as observers. We just think of that little thing as that's the galaxy, but really the whole galaxy includes this gas picture, which is much, much bigger. And one of the things you can note is that there are just as many pieces of information morphologically in the gas map, at least, as there are in the stellar map here. So the number of resolution elements, radio is typically a lot lower resolution than it is in the optical. Optical is smaller wavelength, so you can make sharper pictures. But it is about the same quantity of morphological information. And anecdotally, we know, and we can also figure out that gas has, for instance, pressure effects. There are lots of effects visible in the gas that, for instance, are not visible in the optical. Gas is quite sensitive to tidal effects. Gas is quite sensitive to ram pressure stripping. Like there's other morphological things happening in the gas. Oh, cool, maybe we can use these morphometrics there as well. Now, that kind of then goes right back into over what area do you compute this, right? Because that's the depth of the image. And so the orange line, the red line here, for example, is what we think is the optical disk. The blue line is what we think of as like the edge of the H1. So that's a big difference. So suddenly you have, in the case of gas, you have lots more elements that you can compute morphology over. But if you start doing that, for example, with the optical image, you're basically adding lots of sky background to your signal. And so you're adding lots of murk and noise to your signal. So deciding over what radius do you actually compute these morphometrics is sort of like a ground level, great place to make huge mistakes right at the start kind of thing. So I did this back in a decade ago now. And so do this across wavelengths, right? See how this changes for these two different apertures, for these two different galaxies. We take an isolated galaxy, and M51 is, the canonical interaction. And you see that these morphometrics change with wavelength. So if you want to compare like a UV interaction like in 51, these like the concentrations are much lower, and so don't compare to the optical one because the optical. So there's a clear wavelength dependence, but there's also like, hey, look, they look different in the H1. The H1 knows a little bit about this, so you can actually walk through UV, optical, near infrared, far infrared, and then the 21 centimeter radio. And so I tried to see if there's any difference with morphology and the amount of tidal interaction, and it's really hard to say. Like, did I throw too much information away, or are things too quiet? I love the fact that I had this pun, things are too quiet. Things were actually selected to be nowhere near each other, and there not being a lot of mergers. So basically, they're all roughly at the same amount of interaction, except for M51. So basically, there's one example of an interaction, 3:1 in mass ratio, so it's not even a major interaction, and everything else is basically an isolated disk galaxy. So let's look at more interactions. What you can also do is, this is what Matt and Bass did in 2020, is like, hey, let's add the dust, for example. So you can actually see this as a function of wavelength again, and this is also the thing sample, but now run all the way to 500 micron instead of the 21 centimeter. So it's sort of filling in that far infrared gap to see what the morphology, how that evolves with wavelength and for different kinds of galaxies. So it's quite interesting to see that, for example, if you have a star-forming disk galaxy, yeah, you're going to see that in the dust as well. And so, yeah, you can do this somewhat in H1. The problem with H1 surveys is that we don't have really big ones just yet. Even for nearby galaxies, the all skies surveys didn't have the resolution up until just about now. And so all the prep work was basically seeing if we could do anything with what we had, but you've got Elvis, Viva, and Halo gas. Viva is a cluster, Halo gas is field galaxies, and Elvis is a southern field galaxy. So the selections are a bit different. They're all different instruments. They're all different resolutions. They're all different depths. You can see where the problems are going to get started. These are all asymmetry values of some description, because you also have kinematic values. So you can say, okay, I'm going to define a kinematic asymmetry, or just a morphological asymmetry. The problem is that these are all different surveys. So it's this poor grad student tried to do this comparison. And he got somewhere, but it's quite tricky. So it's better to do this within a larger survey. So here's one, WISPs. That was the biggest H1 survey to date. They are definitely being overtaken now, but at least at the same depth and resolution. And so you have the same parameter space, morphological parameter space, and now in H1, now in gas, right? So we have concentration, asymmetry, Gini, N20, and we have all these points distributed throughout. And we're going to go look for different morphological things like lopsidedness, which is basically, you know, if you've got a circle, lopsidedness is basically, it's blobby on one end or the other. And no, there's no good way to find that. Can I find mergers with H1 morphology? And the answer is, look, at least, you know, perturbance, and especially looking for like low mass interactions. So not the one-on-one interactions like Milky Way plus Andromeda, you know, smash them into each other. We're going to see it. What I'm interested in is like we take Milky Way and like we just skim it with something like the Magellanic Cloud. We just throw a small galaxy into it. Can we actually find those? And the answer is, these are the criteria from the literature, and these are H1 criteria. And so there seems to be a way that you can do this. And where does M51 lie? Like even M51, the canonical merger in the nearby universe, does get selected, but not every time. So that's a good way to remember that even if you've got a criteria, things are going to scatter either way from that criteria line. Oh. So how long are these things visible? So you have to go back to the simulations and see you've got all these values for your concentration, asymmetry, smoothness. And then you take, once again, simulations, and only simulations just got good enough to start giving me a gas map as well as a stellar density map. So we had the gas maps and do those morphometrics on the gas map as well. As you can see, the gas map is radically different from what you see in stars. And so those were a couple of movies that didn't play, so never mind. So same thing, but now also with a gas map. And so you have an isolated disk that just sat there for 3 gigayears, and then do emerging disks, same initial conditions, but now you throw a galaxy at it, right? And so the H1 morphologies are radically different. And so you see that the isolated disk stays, for instance, with a low asymmetry, and then the asymmetry spikes as the merger happens. So H1 seems to be pretty good at this kind of thing. So N20, same thing, isolated stays mostly the same, and then, you know, it does do star formation, so the gas does get, you know, moved and rotates. Stuff happens, but it's not like a merger kind of drastic change. So you see the same thing with GM, which is another parameter that I kind of tossed in there. And so as you look at these things, you you do many simulations. You see the isolated ones are the green ones, and the simulated mergers are the black ones, and with different ratios. And you can see that there's quite a big difference. And they get selected for about a gigayear out of the 2.5 gigayear that the whole thing ran. So in gas, it's about visible twice as long, which is important because if you get like a really much higher merger fraction, you go like, wow, 20% instead of 10% of all galaxies are merging. It's like, yeah, there might be a higher fraction, but you see them twice as long, so the merger rate that you get is still the same. And so the selection of first and second pass, that's pretty much like what Jennifer Lotz found, is like that's when you really see these morphology changes. Then you really see that it's a merger. So in simulated space, you still find you do select them for a certain amount of the time, and various criteria seem to work for these different morphometric spaces. So these visibility times, that's important because fractions are interesting. So you can find like 20% of the galaxies are merging at redshift 1, 30% of them are merging at redshift half. Suppose you see that. Is that an increase or a decrease? Well, it depends on the wavelength that you observe them on or the methodology that you're using. So because then you can tell how long a merger is visible to you. That visibility time is important. And there's a lot of variance in it. So doing that, I did get something that is consistent with the local merger rate, because again, these are all local galaxies. But the interest here is that with the Meerkat array and with the square kilometer array, of course, we can see this gas picture extended all the way down to, redshift 8. So we're getting H1 information from all these galaxies, and it will be interesting to compare the morphologies. And so yes, then we're going to do morphometrics. You can also do other things. So you start combining the information from radio with, for instance, optical. Because I showed earlier that, the line that you draw around your galaxy, this is where I'm computing my morphology on, depends that's what the values depend on, like that initial decision. And it sounds always like pretty clear, like, well, this is the galaxy. But especially if you're in the ultraviolet is basically the galaxy you can see here is the black dots is the ultraviolet. The galaxy is a collection of loose points. It's not a smooth distribution of light, not at all, because you've got star-forming regions and sky. That's it. You look almost through the galaxy any other way. So it's hard to determine which one of those loose points still belongs to this galaxy. So if you go through this and you find, oh, that one, like if you, let's say the one over all the way at the top there, is you go like, you find a little blob there and go like, is that a background galaxy? No way to tell until I take a spectrum. So you have to either take a spectrum of all the little blobbies and say these ones belong or they do not, before you can draw a line around a lot. Now, what I found is that the easiest thing to do is to go to the H1 map. So that's the blue contours, and say, pick a blue contour. And that's the extent of your galaxy. And that turns out to work quite well. So the red dot that you see here is the outermost H2 region that belongs to this galaxy. And so because this all started with like an offhand remark by Dave Thilker, which was that, oh, if, give me the galaxy picture and I will predict the H1 map, because the H1 map and the UV map, the gas supply and the star formation seem to follow each other around pretty well. And so you can use the H1 contour as the outer region for if you want to compute morphometrics for the ultraviolet. That seems to work pretty well. And so these full catalogs are now becoming available. So we have like Galaxy All Sky Maps, and we are getting H1 maps at fixed contour depths and resolution. So we can actually say, hey, we can combine those two and get a quantifiable UV and H1 morphologies. So the neat thing is that you can then start computing concentration and H1, for example, in both the far ultraviolet in the galaxy image and then in the H1 image as well. And so you end up with, okay, there are extended H1 disks and there are extended ultraviolet disks. And the XUV disks, that was totally a visual classification up until very recently, but you can use morphometrics to catch those. Now, I want to emphasize that, again, it depends completely on having like the same depth and the same spatial resolution throughout your survey. So if you have a UV survey, that has to be uniform, and then you put a uniform depth H1 on it, then you can start selecting these things. But it is interesting because an XUV disks with ultraviolet star formation in the outer parts are interesting because we think that's where ongoing fueling is happening. So if you want to see how many galaxies are still getting refueled in a particular volume, for example, so you can look at a cluster of galaxies and say, I'm seeing no fraction of UV disks. Basically, the cluster has stopped refueling, has prevented galaxies from refueling from the gas that's trickling in from, usually trickling in from the outside. Because intergalactic space is not completely empty. It has gas clouds, and those gas clouds are slowly falling into the gravitational wells that are galaxies. So galaxy refueling, ongoing refueling, like how much is happening, that's a question that is outstanding. And so finding a quantitative way to fish out how many XUV disks there are would be interesting. And this seems to be a pretty good first cut. where you could at least find like, so 80% included, so, and 50% contamination. That's not bad. As long as I know that that's the case, then I can calibrate for that. So summary, morphometrics, it's a seemingly straightforward. Seemingly is doing a bit of heavy lifting there, because seemingly means that, yes, these are easy to compute and easy to mess up. You can compute them very straightforward for your survey, and then within your survey, you can use them to classify things. You can turn complex morphology into a few numbers, and that's the attraction, because it's much easier to plot 3 numbers for 50,000 points than to classify these things and then by eye and try to do these SAB or like do a 50,000 point Hubble tuning fork. But it really depends on the depth, the physical resolution, and the wavelength observed. If you mess with that, and if you compare something that doesn't have the exact same depth, physical resolution, and wavelength, you're comparing, or no longer comparing oranges to oranges, and it's basically an orange, or an apple dressed as an orange, and it's probably going to mess with your results. So it's very difficult to compare between different surveys. It's doable, it's totally doable, but you need to calibrate everything out. The broad discriminant is really great. So you can actually say, these are disk galaxies, these are spheroidal galaxies, those are mergers. That seems to be working very well. And now typically we sort of combine this with Sirsic profiles and this morphometric space, and that gives us like a vector that says, this is my, it quantifies my morphology. It turns my morphology into basically 8 numbers. And that's the kind of thing that you can use for machine learning. So that's the thing that I will talk about in a few weeks, where this sort of were the first baby steps of astronomy as a whole to turn galaxy morphology into numbers. Well, guess what? That's exactly what machine learning excels at. So we've been using either these parameters or the images to turn them into morphological numbers. So this is the kind of stuff that you feed into machine learning. So, and it also might be useful to identify rare or just plain strange objects, right? If you have 50,000 of these and you've run them all automatically through your morphometrics catalog, and suddenly you have an outlier, let's go have a look at that outlier. It could identify things like star galaxies, like you have a lot of those, but you can also have like, so you get rid of the stars, and then you have all your galaxies, and then you have rarer things like mergers, and so you can identify those, or you can identify XUV disks, or you can identify maybe some other strange object that pops out because it is an outlier in the morphometric space. So that is galaxy morphometrics. I am proud to say that this is one of those terms that I'm trying to get going, but I think this is a better description than non-parametric galaxy morphology. I think it is a morphometric. And so that's what we've been calling it lately, which is great. And with the new surveys, things like DES, things like LSST, I'm expecting that people will use this as part of their toolbox in order to deal with simply millions of galaxies to turn them into like quantifiable morphological features. All right. Thank you so much for listening. Are there any questions I can answer at this point?
Yeah, thank you, Berner. Yeah, it's good to put this into into some numbers, right? But is the next step then also figuring out why these numbers appear? So look into the physics behind these numbers.
Right. So linking observational numbers to simulated galaxies, for example, it's always tricky to do that. So about 10 years ago, 15 years ago, the simulations could reproduce the stellar mass function, for example. Like if they managed to get the same number of big galaxies versus small galaxies in a given volume, they were happy. What they looked like, they were all blobs, right? They couldn't resolve it was hard to make a disk 20 years ago, right? And to make a disk and keep it, that was the big trick. But they've gotten a lot better. And so tuning the subgrid physics, as this is called, right? So the prescription within the resolution element of a simulation. So simulations are, and let me back up for a second. Simulations never track individual stars because an individual galaxy alone is 300 billion stars. So for a merger that you just saw, you have to track a billion objects in 3 dimensions plus mass plus velocity vector, which is another 6 parameters. So every single object that's a trillion, 6 trillion pieces of information that you have to keep working on. And then I haven't introduced things like that's just the N bodies, right? That's just stars. And if I then toss in gas, gas knows pressure, gas has shocks, gas has other things that happen to it. So you cannot individually track all that stuff. So you have to sort of smooth this out. So you basically, the resolution is now 10 to the 4 solar masses. So basically 10,000 suns, that's your one data point. And so that's the resolution that most of the galaxy morphology is pretty good at. So that's already looking pretty solid. And then you throw in gas, because gas is hard, but it also does everything in a disk galaxy. And so if you you end up with a stellar mass map that you then compute how that looks like in K-band, for example, and then you have a gas map and you compute what that looks like in 21 centimeters. Then you want to compare what you made, that pretty picture that you made, to what people see, right? And so having these morphometrics, you can say like, well, I'm getting the concentrations right because I've got like this cosmological volume, I've got a certain resolution, I've simulated 3,000 galaxies, I've got 20,000 galaxies, and I've got this histogram of concentration indices. What does that look? How does that compare to SDSS? And so that's another statistical test that you could do against surveys. So comparing your big pile of simulated data to your big pile of observed data, and as long as everything is in the same physical resolution, same filter, and same observed depth, yeah, we're good. Then we can see if we got all the physics right. Or if and then I have 3 iterations of my simulated galaxies. I've got one where turn the supernova all the way up to 11 to like, I have no supernova at all. Those things actually mess up the gas disk at a prodigious rate. So you end up with an incredibly holy disk, all these gas blown into it. And it's like, hey, how does that compare? Do I still see that in my morphometrics in the gas survey? So it'll be really interesting, but it's just one other tool in the box to work with this. We needed to turn this into numbers. SB doesn't help. So yeah.
Yeah, no, that's just, you have only 3 different classes there anyway, right? Because you take the bulge compared to the disk, and that's it. And so if you put this into numbers, even if it's just a mathematical tool, that describes it much better. What really impressed me here were the simulations with the gases, because stars honestly are kind of easy, right? Because stars, they live for billions of years. They don't do much. They do, their gravitational interactions, but gas is so much more dynamic. You have to deal with the Jeans mass. The Jeans mass changes because you have pressure, you have different temperatures with it, and then you have star formation. You create even more stars. I mean, this is totally complicated.
So all of that, what you just described, basically gets compressed in a bunch of prescriptions. So it does not happen that you compute the Jeans mass for every pixel in your simulation every time.
Right.
But you sort of tag every pixel in the simulation, like it has this much gas and this much metals, and then it's like, if it hits these conditions, it has this probability of turning into a bunch of stars with this IMF, like this comes out. And so then you have like a very coarse map of a galaxy, but then you also have to ray trace everything. You've got your O stars here in the middle, and you've got like this thicker disk of G stars around it, and then dust that follows to denser concentrations of gas as well. And that reprocesses about up to 70% of your starlight. So it depending on a wavelength. And so that completely messes up your morphology. So you need to do that post-processing steps. That was what Jennifer Lotz did with her simulations. That was so impressive that she used those and then post-processed them to the point that they looked like believable galaxies. Like they had dust in them. They had the right filters, they had the right sky noise, they had the right resolution. And so you can, it's like, yeah, as it turns out, you can still see the morphology there. It was quite a brilliant paper. So I think like this sort of, the morphometrics has had their day, because now we're running headlong into basically AI, having AIs do this for us. But sorry, they've stopped being like the newest thing on the block. They're now basically just a tool in the box, and like, oh yeah, we can compute the asymmetries for these and then see what we get, right? So that has become quite a bit of an industry. So getting 50,000 objects like this is no longer a problem. And so you can compare those to, say, the kinematic measures that you also can get. Like you can get those pretty quickly. Like, oh, which one of these has a big velocity dispersion? Oh, they're also asymmetric. There you go. So you have like multi-dimensional parameter space where you can start defining mergers in and things like interactions, or just can I actually start identifying lopsidedness using something other than eyeballs? Because subjective is never great. And if it's one person doing it, that's also just cruel if you've got 50,000 objects. I mean, it is the kind of thing that you could do as a grad student, but it's not a fun way to spend your time. And so having a way to, just broadens the morphological parameter space. But with caveats, as you can imagine, right? If you start, if you compare to like even a different author or a different survey, there's going to be an offset. There's biases. So caveat emptor. Any other questions or remarks? Okay. All right. Thank you all for coming. Yeah.
Thank you, and see you next week.
See you next week.
You.
And